Hello. There we go. Okay.
Hello, there we go. Yes.
Thanks, Kathryn. So Kathryn is going to be talking about their Google Summer of Code and now master's thesis per project perspective, generic programming user using higher kinded data. Kathryn's been a long time enthusiast of type level and generic programming, and I helped port Shapeless 2 and Scala 3. So thanks for being here, Kathryn. Go for it.
Yes. Let's see if I can screen share. Select. Okay. Let's see. There we go. Right. I can't see my screen, the conference screen while this is going, by the way. So please notify, I guess, Discord if something's up. Anyway, so I will be talking about perspective and generic programming using higher kinded data. We will get to what all of those words mean in a bit. But first off, just quick, who am I? I go by Katefix in most places. That includes this GitHub, Discord, Scala contributors forum, whatever. Freshly graduated from university, and I now live in Denmark and work for KSub AS. If any of you are made Discord bots, you might have used my library Accord. It has nothing to do with this talk, but to mention. I also tried to support shapeless 2 to Scala 3. It worked fine for the core, I think, but it sort of failed. Scala 3 failed to compile some logic programming stuff correctly. So I ultimately think it failed, and when I went back to it recently, it didn't work then either. So sad state, but that's how it is. Anyway, Owen, yes, I am weirdly fascinated by higher kind of data, which we will get to. So what is generic programming? When I say generic programming, some of you might think about this stuff. Type parameterization and such. That is not what I'm talking about. I am more talking about this stuff. Stuff like automatically deriving a type class for product and some type. There are other examples of generic programming I could bring up, but this is the one I assume most people are familiar with. And it is also what we will be talking about for most of this talk, most of it. So how do you do generic programming? Some of you might be thinking of shapeless now. We will get there and we'll talk about it, not too much, but we will start simpler. So first off, we need a skeleton of sort, something to build stuff onto. In Scala 3, this is something called mirror. It exposes types needed for generic programming in the form of tuples and such. It exposes some functions to convert a tuple to the destination product type. It exposes lots of functionality like this. If you're in Scala 2, you have to rely on another generic programming library, which provides a skeleton for you, or you have to use macros. Mirror is unsafe. It can be used directly, and some libraries do, but other libraries like Shapeless Tree and Perspective are also built around it. So, first step that we will talk of is what I would call list-based generic programming. What is that? It is a very simple way to conceptualize and teach generic programming. No macros needed, no mirror needed. Instead, we're just going to use lists. So let's say we have a 3D vector like this, representing a location in 3D space. And we want we can define some members to convert this data type to and from list. So we can convert it to a list, just storing all of the elements in the list, and from a list, taking those elements from the list. We can also define a list of the field names, like this. Now, let's say we want to derive an instance of show using the members in vector3's companion object. So this is the definition of show that we're going to use. And we can convert the vector3 to a list, zip it with zip the values with the field names, map the two of them together, and then comma separate them. So which is what this code does here. Very simple. We just call value.show with show instance of double. This is very simple, but doing it by hand would probably have been simpler and easier. The advantage of this, though, is that we didn't really use much about vector3 itself. We used its type name, and we used the stuff in its companion object, but nothing about vector3 itself. Which means that we can abstract it out and take those things in as parameters instead. So we can just work on any type B instead of on double, which is what vector3 worked on. We take in a show instance for this type B. We take in a toList function. We take in the list of field names. We take in the type name. And with all of this, we just do what we did before, but now more general. Now, carrying around all of those things can be tiresome. So we can make a type class to keep them together and not have to think about passing all of these things around. We see here that we have a function here that converts to list of inner, where inner is the type of the fields, for example, double here. And then we have another function called from, which converts from the list of inner to back to our type. I will call the list of inner here the generic representation. And a type class which exposes functions to convert to and from a generic representation. List of inner is just one possible generic representation. I will just call these generic type classes. So we also have, for our generic type class, a list of the field names and the type name. So using list generic, we can rewrite our code a bit to just clean it up. We call gem.to instead, zip it with gem.field names. We use the type name in gem. Also, we use the path dependent type here to get a show for the field type. So this works fine, and it's very simple and such. But it does have a few problems too. First off, it requires all of the fields to be the same, and that is not true for most data. So not ideal. It is also unsafe. Nothing prevents the user from passing in a wrongly sized list to any of these functions. And list also uses int indices, which are not bounded by, like, you can pass in 4 to this and it will just crash at runtime, and we do not want that. So the obvious solution to this is just store everything on the type level. And that's where we get H-lists or heterogeneous lists and shapeless 2. Which shapeless 2 is the one that takes this approach quite commonly. And so what is an H-list? An H-list is basically a list linked list that also stores the types of its elements at the type level. So we have cons and nils. Again, cons looks a bit different in that it has two type parameters, the head and the tail, and then it stores both of these. We could use it like this, for example. We have an ISB type here, which has an int, a string, and a boolean. We can construct an H-list representation for this, which is int, and then string, and then boolean, and then nil. So we can then have function to convert to and from this representation. We can't easily just forget about a field here unless we forget about it absolutely everywhere. This is also completely safe. We cannot pass in a list that is too short to from H list, for example. It just won't compile. So everything is perfectly safe and wonderful, maybe. So we want a generic type class for this. Shapeless calls its generic type class generic. I guess that's the advantage of being first. It also keeps the name of the type in another type class called typeable. With this information, let us go and derive a show using this. Will it be the same as before? No, it will not, because Shapeless uses type level programming to define type class derivation. So we need to do some induction over our H lists. So here is how we can do it for show. So first off, we need our base case, which is the end of the list. That is equivalent to an empty string. We also need our induction step, cons. So here we show the head, and then the tail, which is the induction hypothesis. Lastly, we need to define an extra function to bridge the gap, so to say, which converts the input to an H list and start the derivation. Also to note, we do not touch on any of field names here. That is too even more complicated stuff here. So Shapeless has some good advantages and some problems. First off, it is wonderfully safe. It solves all the problems we had around soundness and safeness of lists. It is also really expressive, provided you have, but only if you're willing to use logic programming, which is what we just did, which might not be familiar to most Scala programmers. It is also slow to compile with Scala 2, being O(n) squared in the size of the case class you're working with. Lastly, as anyone that has done type level programming, they will know that debugging errors for type level programming is not fun. It is a chore and just can boil down to the compiler just screaming at you, something is wrong. It's gotten a bit better since then, but it's still not fun. So that's where my solution comes in. I'll start deal with high kind of data. So Perspective, my library, wants to get back to working at the value level, no type level programming, and to use simple functions like fold and map, as we saw in the list example. The closer we get to that list example, the better we've succeeded in the better Perspective succeeds. To do this, Perspective looks to where these functions come from. Type classes like function, a functor, applicative, verse, and so on. So if we go back to the list example, what was it that was so nice about it? Was it the list, or was it the operations on list? I will say that the list was the source of all of our problems, all of the unsafeness. If we could have the operations without list, that would be wonderful. And we can. We can parameterize a vector tree with the type A and store just A's instead of like doubles. We can get back our double vector tree by just applying vector tree of double. With this, we can then have our field names, which is just a vector tree of string, where we store x, y, and z. With this now, we can define an applicative and foldable instance over this, shown here, and we could rewrite our example of show derivation as before, just using applicative and foldable instead. So wonderful. Except we haven't solved the problem that our data type can only contain one type, and in fact, it seems to have gotten worse because we are using type classes that kind of require that it only has one such type here. So how do we get around this? We add more types. In particular, we add a higher kind of types. So this is what higher kind of data is. This is what data looks like normally. We have an int, a string, and a boolean, which has the type int, string, and boolean. If we instead parameterize or type by a higher kind of type and wrap all of types in this higher kind of type, we get higher kind of data. So we, instead of int, string, and boolean, we have f of int, f of string, and f of boolean. And this we can define type classes for. Now, we're going to have to define our own type classes because cat's type classes do not work with higher kind of data, or well, higher kind of types. And you might say, doesn't cat's MTL, or I don't know what it's named at this point, have types that work with higher kind of types? Yes, to a degree, but not all of them, and not it's missing a few. So perspective just goes all in and defines its own types. I'm fairly certain you won't find a foldable type class, for example. So before that, we want some extra types to make defining these higher kind of type classes a bit easier. The identity, we have first the identity type, which just maps all types to itself. We have the const type, which just ignores the type that we give it, like the const function. And then we have higher kinded arrows here. We also, perspective also defines two syntactic subgroup, I guess, variants of this arrow. When one side of the arrow is not higher kinded, and that the side of the arrow that is not higher kinded is the one where we have hash. So here the hash is on the left, and so then the type that is the not higher kind of type is on the left. Same for the next one. With all of that in mind, we can finally actually get to the type classes itself. I won't go too much into these type classes. They are mostly the same as you might know from cats already, except for high-kinded. To note here is that the type of a high kind of type here is slightly different from what we saw with the high kind of data. This is to allow some more flexibility and stuff. We can just perspective defines some aliases that ignores this second type. and all these aliases are suffixed, with C. So foldable K is higher kinded foldable. Foldable KC is a higher kinded foldable that ignores the second type here. So next we have functor. Functor gives us a map operation. We also have apply. Now, why am I talking apply? Where is applicative? Where's monad? That's coming next, right? No, they are not coming next. Applicative and monad are basically useless for our use cases, and applicative will be brought up ever so slightly later in the talk, but monad is just straight up useless, and also it is weird. What I said before about if you understand the non-higher-kinded type class, you understand the higher-kinded type class does not really apply to monad in the same way. Anyway, apply gives us a map2 operation. So given an FA and an FB, we can take a function A, B to set and produce an f of z. We also want traverse. Now, defining the composition of two types is slightly, it's not as nice when you go a bit higher. So we need a type here to just make this simpler for us. Other than that, though, traverse is mostly what you've seen before. Given an f of a and a function from a to g of b, it produces a g of f of b. We also have sequence. So given an f of g of a, we can instead produce an g of f of a. Traverse is nice for stuff like validation, or when something returns either or option. For example, if you are decoding JSON, you get an either string or the value you're working with, for example. Now, with all of these things, we have all of the fundamental building blocks to start writing type class derivation code again. So let's derive an instance of a show using perspective. So we are going to use apply and foldable type classes. So we need to get those in. We need the type name as before, the names of the fields, and the instances. Now, here is something, what happened here? So the type name is fairly simple, but the names of the fields might not be so intuitive. So what we're doing here is that we are taking f of const of string. That is basically the same as our vector tree example where we only had one type, except with const we can basically do this at will, opt-in, instead of just being forced to always have one type. So this is our case class as just a bunch of strings. Now we also have f of show. And this works because type classes in Scala are first-class citizens. It is not a fact that you see used much at all, but they are. And that means that we can pass them around as values, we can store them in fields, we can do anything that we want with them that we can do with normal values. And that includes sticking them in our higher-kinded data. Lastly, we return f of ID because, as I said, ID, the identity type, maps all types to itself. It is what we use when we just want our data not in a higher-kinded form, basically. Higher-kinded data form. So what we do then is that we take our type class instances, we map them with the values, and for each field value, we show that field value using the type class instance. Next, with I should say map to const. We use map to const because the Scala compiler doesn't quite like to enforce const types, so we need to help it along a bit. Anyway, with these showed values, we then go and map that together with the names to produce a name equals value, as we had before. We convert this to a list, which is a function that comes from foldable. And then we just call make string on this. And then we just add a type name with elements. And this is mostly the same as what we had with our list example, which means that we're already quite close to what we want. But this has a bit of a problem. Our type class derivation code, we want it to be fast. And just like and this is actually a problem that our list example had to a degree too. We are iterating over our data too many times. We should do this in like 1 or 2 passes, but and each map 2 is another iteration. We should not do this. So how do we fix this? We use a type class called representable. You can find representable in cats. It is not that common of a type class to see around. It basically exposes functionality, for us at least, similar to list.tabulate and list.apply. So it allows us to index into our type safely. So it does this by finding a representation type here, and it requires that there is an isomorphism between the values of the representation type and the fields of the type we are working on. So we have a function tabulate here, which for each index, we need to produce a value of that type. And if we do that, we get our high kind of data here, for example. We can also just have get our indices as an f of representation k. And then lastly, we can index into our type. So given an f of a and an index to the type c, we can get an a of c. So here is an example of how we might have what a representation might look like. So given some higher kind of data, ISBK here, this is a possible representation here. So we have, for the int field, we have an int field value. For the string field, we have a string field value. For the Boolean field, we have a Boolean field value. Now, you don't have to use an enum like this. You can also just use anything else, which, as long as there is an isomorphism between the fields and the values. But yes, using this, we can now again derive show, but more efficiently this time. So we are using f representable here instead of apply. So we call after tabulate. So we have our index type here. Then for each, then we can get a value by calling an index on our values. We can then get a field name by calling index on the field names, and we can get our type class instance by calling index on the type class instances. And then we can just do all of this combination in one step. You can improve this further just using fold instead, but this shows the basic idea. So up until now, we've required that all code also be higher kind of data. This is a stupid restriction, and we do not want it. We do not require that all like shapeless stuff is implemented in terms of HList. So we don't want to require high kind of data here either. So we can define a generic type class. Perspective's generic type class is quite complex, and this is a simplified view of it. Anyway, so for a type A, we have our high kind of data gen here. We have our index type index. We have the type name and the names, which are stored both at the value level and the type level. So we have type name and the names, gen of const. We have function to convert to and from the higher kind of data representation. So we have two, we have going from A to gen of ID, and from going from gen of ID to A. Lastly, we have type classes. Using this, we can just clean up our code a bit. We take in an HKD product generic instance instead. If there exists a type class instance for all the fields of the higher kind of data representation, it will also just automatically find an implicit instance for the whole thing, so to say. So requiring instances like this is also just completely fine. We then call tabulate over this. Product element ID is a new function here. We could call gen.2a.index k index. That will be slow because it will require us to convert the entire thing to the intermediary representation. What we can do instead is that we can just use the wonderful function called product element found on product, which is completely unsafe, but Perspective gives you a nice, safe facade around it. So this is just fine. So this works fine for product types. It works wonderfully for product types. This code is like quite close to what we had with the list-based example. So how do we translate it to some types? Because some types are hard. Why are some types hard? Well, we need some sort of map to function on either A, B. Now, that's simple, you might say. Doesn't CAS already have that? Well, yes, it does, but it's biased. And we want something that is not biased. Now we're getting to the hard part. So let's try and see where we get stuck. So we have a type either k here of f of ab, which is an either f of a or f of b. We want a map to k function. So either k a of left or right, or either k b left and right. And we want to have a function from a, b to z. Now, if we have a left and a left, this is quite simple. We just take the left a and the left b, and we apply the function to them. The same applies if we have a right a and a right b. We just apply the function to them. But what do we do if we have a left and a right or in some way? Well, we can't. Any solution here would go up against, will either make it biased or just run up against applicative laws. So why don't we do the simple option and just wrap everything in option and just return none if we don't have an answer? Surely that can't work, right? Well, it does. This works just fine. Using this, we can define an apply over or either type. We cannot define an applicative type. This approach does not work on applicative. And yes, this is where we talk about applicative. So how do we work with applicative here? Basically, what we need is that we need some type like either, but which has both values at the same time. So, and inclusive all types, like cats.ior, which can be, for example, defined like this. It is special in that it has a third case, a both, which is both the left and the right at the same time. Using that, we can just implement applicative as some ior.both and then add a value. So in fact, this type is like option of ior is very special because it's a sum type that we kind of intuit, but it's also a product type at the same time. And product types we know how to derive for, sort of. So here is a proof to just show this too. We have two representations of option of iork. We have the product representation, which is just option of f of a, option of f of b. And then we have the sum representation, which is left k, f of b, right k, f of b, both left f of a, f of b, or neither. And then we can convert between these just fine. In effect, this basically means that we can have our type, have our generic type, which looks like this. Instead of the identity type, we instead use gen of option here. So 2 produces gen of option where all the fields are none except the one field which we do have, which is sum. From meanwhile returns a sum of a if one and only one of the fields in gen of option is present. If more than one is present, it returns none. If less than one is present, it returns none. So here's a short example just to show how high kind of data for some types can work. We convert our sum type here to its high kind of data representation. We then fold over this value. We get the value here. This is going to be option of some subtype of A. We get our type class instance. Then we fold over this option. If it is none, we just return an empty string. If it is sum, we show it. So, time for some slides that were added at like 30 minutes ago. Let's go. So, Perspective also has some code to do this, but with inline and macros instead, which can generate extra efficient code if you want it. It looks mostly the same as what we've seen before. The time class instances are gotten slightly differently. This is not a true polymorphic function and so on, but it mostly works the same. This will basically generate code horrifying for us functional programmers code like this. We have arrays everywhere. We have a while loop. We have mutable variables. But you know what? It doesn't matter because we do not have to think about this. This is the code we write, not this. It just generates this nice and efficient code for us while we write it in a functional and immutable way. Now, sometimes we just want to go even faster. I do not have a show example for this because such impromptu inclusion in the slides. But sometimes we don't want to box values when we're deriving type classes. Most type class derivation stuff currently does box all elements, but Perspective has some very hackly cobbled together stuff to not do that. So we call tabulate fold left, which is tabulate on the indices basically. And we call unrolling equals true. This is a special parameter just for the inline module of perspective. We then have access to a few new functions. So we have access to gen.late inline match, which is like inline match, but it expands slightly later to be useful for us. We also have a.product element ID accept, which will select our value by its field name and field name instead of by its index, so it will not box. So what does this produce? It basically produces the same code as you will as if you've written an JSON encoder by hand. This is what it produces. It is very efficient, at least for small case classes, and very inefficient at compile time. Let's talk about performance. Perspective lies mostly the same as everything else here, except shapeless 2. This is product type Scala 3 performance for encoding and decoding JSON products. Things mostly work fine here. We have the unrolling module, which is almost as fast as handwritten code. Other than shapeless 2 here. Yes, this is for Scala 3. I used the core port of the shapeless 2 stuff that I ported to Scala 3 to benchmark it. It doesn't perform well, as you can see. That might just be about my port. I don't know. We also have compile time. This is for Scala 2 and Scala 3. As we can see, perspective performs really well for Scala 2. The only real competition here is source derivation, which is absolutely magical and really fast, and writing code by hand. We also see for Scala 2, shapeless 2 being O(n) squared here. I do not know why it is that, but I do know that if we go over to Scala 3 here, it goes away for some reason. For Scala 3, we also do see that the inline and unrolling modules of perspective are very slow to compile, especially for bigger case classes. I've tried to improve this since the benchmark was done. I'm still working on some stuff, so who knows? Maybe it's fixed, maybe it's not. I don't know. Anyway, we've talked a lot about type class derivation so far. Let's talk about not type class derivation for a bit. So let's just go over some cool tricks you can do with high kind of data with this. Let's start with validation. So we have a validate type here, which checks if a type is valid and outputs a validated null. So we have some checks here. We can check if it's not negative. We can check that something is not empty, or we can just say it's always valid. Then we have some high kind of data here. We can construct a description of the validation that we want by just constructing an instance of 4k for validate. So we can just say the first field, make sure that it is not negative. The second field, make sure that it's not empty. The third field, don't worry, it's always valid. Another example is that we can do SQL query data stuff. This is actually what I initially did to get me on the high kind of data train. For some case class 4k here, we have some fields. We can define a table for this, table representation of this, with some columns, the names of these columns in the database, the types of these columns in the database, and then we need some boilerplate to just work with higher kind of data volley too. Using this, then we can do some SQL query generation. We can insert some fields into this table. we can insert some fields into this table without some of the fields, just using some and none easily. We can select from this table, we can group map from this table, and know that this is statically going to work. If you worked with Slick and encountered bugs around group by, you know why this is really nice. We group by A1 here. We have our foo type here, but this foo is of a different type than it will be in, for example, where here instead. So we need to get it back to the type that it should be, or else our code won't compile. So this is what array aggregate is doing. Lastly, we have some delete here. This is all very early in development code stuff. You can find it on GitHub at patrix.dataprism. I would very much appreciate it if people would give me encouragement to finish this and stuff. Lastly, we looked at some inline stuff. When I showed this to Niklas Stuckey, he said, why aren't you using macros to make this so much less hacky and stuff, and like using multi-state programming and such? I was kind of scared of that idea, but last month I went and experimented with it. So what if we had something like this instead? So we have an expression of A to gen of expression, and gen of expression to expression of A. Can we implement this? Yes, we can. Well, I've not implemented all of this yet, but some of it is implemented. So I won't fit this code in one slide, but basically what we then can do is that we can get the types. This is all just pretty boring code actually, and I'm running low on time. So we have our body here. We have our special expression HKD product generic. We have quotes. We have our expression of A here. We have the types of the fields of this. We have the names of this of the fields, and we have the instances as compose expression of encoder. So we can tabulate over this. Get the value. Product element cat is like product element ID, but more general. So this is then an expression of X. So we have a type of X. We just index into the types. And then we can just check using normal macros if our type is an instance of, for example, int or double and boolean, and then handle and construct macros to do this without boxing, like shown before, but more robustly. Yes. Anyway, that's it. If there's anything I want you to take away from this talk, is that high-kinded data is great and you should use it. Anyway, that's it for me.
That was awesome, Kathryn. Higher-kinded types are sometimes elusive, especially for me, but I think you illuminated a lot for everyone. So thank you.
Yes.
And yeah, if you have any questions for Kathryn, please send them over to Talk Perspective in our Discord. And then we'll get back at 2 p.m. Eastern for the next talk. Thanks all. I'll stop the recording.